ఓకేనమ్మా.
సార్ వాయిస్ ఓకేనా సార్?
అప్పుడు నాకు వినపడతా ఉంది, మీరు చెప్పేది వినపడతా ఉందమ్మా.
ఓకే సార్.
థ్యాంక్ యూ అమ్మా. పీపీటీ ఒకసారి ట్రై చేసి చూస్తానమ్మా.
చేయండి సార్, చేయండి సార్, చేయండి
సార్. నా వాయిస్ వినపడతా ఉంది కదా? రైట్ రైట్. షేర్ కొడతాను. షేర్ కదా, షేర్ కొట్టాలి కదా? అదేనమ్మా. షేర్ కొట్టాను. దాంట్లో స్క్రీన్ 1 అని వచ్చిందమ్మా. స్క్రీన్ 1 అని వచ్చింది. అది ఆన్ చేస్తే ఇది మినిమైజ్ చేసి దాన్ని పెడతానమ్మా. మినిమం అమ్మా కనపడిందా ఇప్పుడు? పీపీటీ ఆన్ చేశానమ్మా. హలో హలో హలో
సార్, కనపడలేదు సార్, కనపడలేదు స్క్రీన్.
కనపడలేదా?
సార్
పీపీటీ ఆన్లోనే ఉందమ్మా. అయితే నేను ఇది చేయటం సరి చేయలేదేమో, ఇంకా షేర్ సరికొట్టలేదేమో.
సార్ మీరు షేరింగ్ అనేసి
నాకు కనపడుతోంది పీపీటీ. మైక్రోసాఫ్ట్ పవర్ పాయింట్ అని ఒకటి స్క్రీన్ లో వచ్చింది
సార్. షేరింగ్ అని కొట్టాలి సార్.
మళ్ళా షేర్ కొట్టాలేమో అయితే. ఓకేనమ్మా.
సార్ నౌ ఇట్స్ కమింగ్ సార్.
ఓకేనమ్మా.
yes sir, yes sir, yes sir.
ఓకే సరే రైట్.
సార్ మీరు అది దీంట్లో పెట్టుకోండి సార్. దీనప్పుడు
ఇప్పుడు స్టాప్ షేరింగ్ కొట్టేయమంటావా ఇప్పుడు? అంతేనా?
ఇంటూ కొట్టేసేయండి సార్. స్టాప్ కొట్టండి సార్.
స్టాప్ షేరింగ్ కొట్టేస్తానమ్మా. నాకు మళ్ళీ అప్పుడు కొంచెం జాగ్రత్తగా డైరెక్షన్ చెప్పండి కొంచెం. నేను రైట్. స్టాప్ షేరింగ్ కొట్టేసాను. ఓకే కదా ఇప్పుడు? రైట్ రైట్ రైట్.
ఫోన్ చేస్తున్నారు. లైన్లో ఉండండి. మీరు వార్డెన్ నంబర్ ఉందా? లక్ష్మణ్ నాయక్ అంటే నేను బీసీ వెల్ఫేర్ చెప్తున్నా కదా. వస్తా సోషల్ వెల్ఫేర్ మరి ఆయన ఎందుకు ఫోన్ చేస్తారు? మీ వార్డెన్ నంబర్ ఉందండి. మీరు లైన్లో ఉండండి. ఇప్పుడు వార్డెన్ కాల్ చేస్తాను నేను. ఇంకా భోజనాలన్నీ పెట్టట్లేదా సరిగా?
లేదు ఆఫీస్ చేశారు మొన్న మనీ కట్టమంటే నేను కట్టమన్నాము అనేసరికి ఆఫీస్
Hello? Hello? Hello?
Sir.
Mama, share. Is it okay, ma?
ఓకే సార్ ఒకసారి వెల్కమ్ అది ఉండండి సార్, ఒక నిమిషం ఉండండి సార్, స్టార్ట్ చేస్తాము.
అట్లా వెయిట్ చేస్తా.
Good morning to all. As one of the mathematicians quoted that math is the only place where truth and beauty mean the same thing. Math is worthy of much exploration and examination because it is intrinsically beautiful, nothing more to say. Why play the piano? Because it is beautiful. Why engage in math? Because it is too beautiful and creative. With this, on behalf of the Department of Applied Mathematics, we are happy to invite for the International Symposium entitled on Mathematical Sciences and their applications to this day, 29th January 2022. I welcome our Honorable Vice Chancellor, Madam, Professor M.Sreedhar Babu. Good morning, Madam, and welcome, and we welcome you, Madam. I also take the pleasure to invite our Registrar, Professor D. Vijayaragha Prasad Garu, In-charge Principal, Professor M. Chandramati Shankar Garu. I extend my welcome to my colleagues, Head and Dean Faculty of Sciences, Professor P.Vasanthi Madam, and organizing members, Dr.M.Sreedhar Babu Sir, Dr.B.Sreenivasa Reddy and Dr.S. Suneetha Madam, convener Dr.G.Kathyayani. We also take a personal gesture to invite our distinguished speakers, Professor Sreenivasa Sir. Good morning, sir. We welcome you, sir. And
Namaste.
Professor
Namaste,
M.
good morning.
Thank you, sir. And Professor N. Kishan Garu. Good morning, sir. We also welcome you, sir. Our most valuable participants, faculty, students, very good morning to all. Now, I request all of you to stand for invocation. Thank you all for coming out. Now, I request my colleague, Dr. Sreedhar sir, to give the brief introduction of the resource person, Dr. M. sir.
What is this?
Morning to one all. It's great to be a student speaker, Dr. Sreenivasa. Dr.G.Kathyayani, retired professor in the Department of Mathematics, SV University. He served as a head and he was chairman. He guided 41 PhD students and one is submitted 26 MPT programs. He received Presidential Award by the Government of Andhra Pradesh, Science City Award, and 5 more awards from various organizations. He has published 205 papers in the fields of flow through, porous media, and peristaltic transport. He worked as an associate professor in mechanical engineering department in Malaysia for 1 year. He visited Bolsman and Bangladesh on academic assignments. He was one of the local organizing secretary for 104th Indian Science Congress and local organizing secretary for IMS 2018. Present, he is an executive member of IMS and AIR Tamil Nadu. I'm very happy, sir. Over to Sreenivasa, sir.
Thank you. Thank you. Mala, share again. I have to share.
We will share it, sir.
Right. Is it visible, madam?
Yes, sir.
Yes, sir.
Yes. Honorable Vice Chancellor, Madam Professor Kalavati Madam Garu, respected Registrar Professor Prasad Garu, and revered officers, university officers, deans, principal, and other dignitaries of the university, esteemed faculty members of Yogi Vemana University, and today's felicity, Madam Professor Vasanthi Garu, Dean Faculty of Sciences, former Registrar of YVU also. I deem it a great honor to be in this program. Dear research scholars, participants of the conference, esteemed participants of the conference, it is a great privilege for me to be associated with this very great function, international conference organized by Yogi Vemana University. We are happy to see this program. Because of the madam's retirement, this program is mainly arranged. And in this program, organizing committee, I thank the organizing committee members, university authorities for giving me an opportunity to share my thoughts on the fluid dynamics in general, the findings, the works which I have shared with my collaborators in general. So, fluid dynamics is a very, very important subject which is related to many fields such as mechanical engineering, chemical engineering, civil engineering, biomedical engineering, geology, medicine, etc. So, in this subject, the main interest is to examine, to investigate the fluid flow, because fluid flow exists in many places such as the living beings, all the living beings will have the behavior that is a fluid flow movement that is there in every living organism, mammals we can say also. And also the fluid flow occurs in the soils, that is in the underground waters we can see. So due to all these important applications, there is a need for us to go for the fluid dynamic flows related to the living beings and also the geological systems. My lecture is confined to the biofluid flows. In general, I am taking, because fluid dynamics is a very, very vast subject, everybody knows. But from the fluid dynamics, I will touch upon some of the important findings which I observed. And I would like to stress upon some of the important properties which occur for biological systems. That is, we can say the elasticity property, peristalsis property, or wall properties in general we can say. And it is a well-known fact that the famous Poiseuille law is done by the engineers, mechanical engineers, who made extensive experiments with different fluids, maybe with water, maybe with mercury, maybe with other polymers, oils, etc. Their findings are reported in literature that we know very well. But the important fact is the experimental observations done by engineers, that is, for example, water flow in a pipe or oil flow in a pipe, etc. They are matching with the theoretical results in fluid dynamics. That is the great thing in the history of mathematics. In applied mathematics, we teach fluid dynamics as one of the subjects, important subjects, where we study flow in a channel, flow in a pipe, etc. This flow in a pipe has experimental background given by two famous engineers, no other than the Poiseuille and Hagen. These two engineers did commendable work experimentally on different fluids regarding the fluid flows. That is, regarding the, suppose if I have a pipe of 10 centimeters length, I can find out how much amount of fluid, that is, we call in fluid dynamics flux, how much amount of fluid can be collected at the outlet. Because blood flows in a human body, we know very well, water pumping connections will be everywhere. The pipe radius will be fixed according to the requirement of the amount of fluid which we would like to have. Sometimes small diameter pipes are fixed. Sometimes large diameter pipes are fixed. In industries also, sanitary pipes are there. So everything is done depending on the flux. That is amount of fluid to be collected at the outlet. Further, on these people, the two people which I am referring, the first person is Poiseuille photo, which we are seeing. He was born in 22 April 1797. He belongs to Paris originally, and he lived 72 years and gave a lot of work in fluid dynamics, a lot of work, commendable work in fluid dynamics. His nationality is French. He is physicist and physiologist also. He is very famous for today's Poiseuille law, who enunciated, who found experimentally, that is Poiseuille's law. Next, let us see the Hagen, another engineer. He is from Königsberg. Everybody knows this has a very, very famous problem in graph theory also, Königsbridge problem. In that place, 1797, same year, a little prior to this Poiseuille, he was born March 3, 1797. And he lived for 86 years, this person. And his nationality is German. His fields of interest includes physics, hydraulics, etc. So these two people are the famous people in fluid dynamics who got laurels to the subject of fluid dynamics. Actually, the idea of Poiseuille is to work blood flow in pipes, actually, and he started working with, because blood clots immediately, different fluids, and he worked a lot on the biology. That is, after his doctoral dissertation on the heart and the pulse waves, these are very, very important. Poiselli worked in microcirculation in hemodynamics. So he did a lot of work in biofluid dynamics, and he did a lot of papers and presented to Amma. Hello?
అది మీరు ఒకసారి ఫుల్ స్క్రీన్ చేస్తారా?
Yes. Slide show bit. 1 minute.
Yes, sir.
Is it okay?
ఓకే
Thank you. In 1839, Poiselli deposited with the French Academy of Sciences a sealed cover containing the results on the water flow in glass pipes, the effects such as pressure drop, tube length, tube diameter, and temperature. And 1841, he made all these innovations. And Academy approved his results in December 26, 1842. So they appeared in Academy proceedings. After his submission, 7 years, it took 7 years for the Academy to validate his work, etc. And this is Poiselli experimental apparatus, just given in one of the Journal of Fluid Mechanics paper, how he made experiments and got the famous Poiselli law. And I was telling about the other person, that is Hagen. He also made very good experiments with different fluids. He also found the law. That is the famous law what we are telling. The Poiselli law now many people are calling. But actually, the contribution goes to both the people. Both people worked simultaneously in two places. The results are, both got the same results. Therefore, people will say that it is Hagen-Poiselli flow for everybody's understanding. And but many books are not using this one. They just say it as Poiselli's law only. So actually, it should be called Hagen-Poiselli's law, etc. That is what the best way. But anyway, it is a general one. People call it as Poiselli's law because Poiselli gave the more clarification or more innovations in that particular area. So that is one thing. I would like to add the result from Guyton. People in medicine will see this book. With the derivation, it is found this law. The 3 is the law, pi delta p r power 4 8 eta e. This is the Poiselli law given in medical textbook. Guyton, the famous author. The people will go through this Guyton textbook for medicine, textbook of physiology, etc. The law is Q is the flux, that is the amount of fluid collected at one end. Suppose if I have a pipe like this, call this as inlet, starting one. The other one is outlet. So the flow enters in the inlet, comes out from the outlet. How much amount of fluid we are collecting from the outlet? So that is the flux which we are always interested. The medical textbooks contain this law. Delta P means suppose inlet is P1 pressure, outlet is at pressure P2. Delta P means P2 minus P1, the difference of pressures between inlet and outlet. So this is the law. Even we can see in the medical textbooks also. Pi delta P R power 4 by 8 eta L. Eta stands for viscosity. L is the length of the tube. Pi is well known to us. Small r is nothing but radius of the tube. We have a tube here, this has radius. So that is the law which we find in medical textbooks also. Actually, this law is given by, I told Poiseuille already. Just I am quoting the law given by Hagen. If you ignore the square of Q, then this goes back to the law of the Poiseuille itself. So therefore, the law of Hagen from experiments and the law of Poiseuille, what I was telling, both are the same. So I would like to add finally, in the fluid dynamics, in the fundamentals of fluid flows, the first and foremost problem is the pipe flow or channel flow, whatever it may be. Here, everybody knows the standard Navier-Stokes equations are used for a Newtonian fluid here. This is the governing equation, 1 by r, d by dr, or d1 dv by dr is equal to minus p by mu. P is the pressure gradient, minus dp by dz I have given there. It is a pressure gradient. The velocity can be calculated on integrating the differential equation, that is momentum equation, subject to the boundary conditions. One is maximum velocity at the central line, other is the no slip condition at the wall. Taking those into account, one can find out the velocity field as p by 4 mu a square minus 4 square. A is the radius of the tube here, R is any value between 0 and A. Flux can be calculated using integration formula, pi times Pa power 4 by 8 mu. When you observe this one and the Poiseuille law given by these people, this is one and the same. The Poiseuille law given experimentally, now which I have shown through the theory, they are one and the same. The flux m, whatever name here, m is proportional to a power 4, that is the fourth power of radius. That is the famous thing recorded by both Hagen and Poiseuille. Two people found experimentally that you can take any pipe, that is A is radius of the pipe. The flux, whatever you get, flux I told you, that is the amount of fluid collected from the outlet. So the fluid flux is proportional to fourth power of radius. That is the greatest law in fluid dynamics. So that is an experimental law which we are able to prove using momentum equations, Navier-Stokes equations, the same law theoretically. I can say that Navier-Stokes equations in one way are verified by this Poiseuille-Hagen experiments. So that is the importance of this Hagen and Poiseuille. Not only that one, flux is here, mu is in the denominator, mu is the viscosity. That is, flux is inversely proportional to viscosity coefficient of viscosity mu. And also, the flux is proportional to pressure gradient. So these are the things what we can observe from this, the famous Poiseuille law. So taking mu changes means different fluids I am taking. A changes means different radii pipes I am taking. Capital P changes means that is I am taking inlet and outlet pressures are different. So in that way, the flux depends on all these parameters, especially in P, A and mu. So these are the experimental innovations also. Now, I would like to say that here P1 I was telling inlet pressure, starting point. Outlet pressure, I was telling P2. Please remember that P1 is always greater than P2. If I want to make water flow in this pipe, oil flow in this pipe, some polymer in this pipe, some sanitary fluid in this pipe, some blood in this pipe, whatever it may be, the main mechanism here is higher pressure at the inlet, starting point, and lower pressure at the outlet. Then only the flow takes place. In terms of delta P here, delta P is negative. That is, flow takes place from higher pressure to lower pressure. So these are the important things what we find here. And I am not going to other details of this one. This Poisson law is extended for non-Newtonian fluids also. And Poisson law is a good approximation for blood flow, provided appropriate value for the apparent viscosity is used. Poisson law is one of the few equations derived from applied mechanics, which is well known to the present medical community. Therefore, we have a lot of regard, respect for Poisson law, importance for Poisson law. So, just I recapitulate now the things like stress-strain relations. I would like to just present. These are well known to you. The Pij here is the stress tensor, and P is the pressure at a particular point, mu is the viscosity, etc. Delta Ij is the Kronecker delta, etc. And standard Navier-Stokes equations I have presented. For a Newtonian fluid, these are presented. If I change the stress-strain relations, which we can have, that is, I can simply say, if I call the stress as say some Pij or tau, whatever it may be, tau I take a symbol, E is the strain, rate of strain. I can have the result tau is equal to mu E. That is the Newtonian fluid I can have. If I have different equations, that is, for example, E power n, we can have power law fluids. If I add some other yield stress, it goes to Herschel-Berkeley fluid, or like this. So different non-Newtonian fluids can be derived from this stress-strain relations. And just I am interested in the Poisson law only. If I take a power law fluid means the stress and rate of strain relation is tau I take as the stress, E as the rate of strain. The result is tau is equal to mu times E power n. That is the relation between stress and rate of strain for a power law fluid. For that, Poisson law is calculated. That takes in this particular form. That is, I am presenting the different forms of Poisson law for different non-Newtonian fluids. This is the Herschel-Berkeley fluid. This is a very good model. People made experiments with cow's blood. Actually, they found that this cow's blood will follow the Herschel-Berkeley fluid model. So therefore, we can classify the cow's blood most often as Herschel-Berkeley fluid. Therefore, people have done good work in this model, fluid dynamic model also. So you can see the flux Q equal to some pi into n by 3 n plus 1 p by 2 mu 1 by n. N is the power law index actually. R power 1 by n plus 3, a function of Cp. Cp is this one, etc. So we have all these things here. Similarly, Casson fluid. This is a well-known fluid, especially most of the human blood is modeled, that is through Casson model. There also we can have the Poisson law in this way, some PR power 4 by 8 mu into h of Cp, where Q by Q naught is Hcp, etc. So this is the regarding the famous Poisson. Again, I will come back to Poisson when I deal with a mathematical model regarding elastic tubes. That we will come back to that one. At present, I am going to another introduction regarding the porous media theory. So I would like to say that porous media theory is also one of the important theories what we know very well. Everybody is working in porous media all over the world. People are working. That is, I can say, undeformable porous media is there. A lot of literature is being there. Many people have worked in South. Professor Udregar did commendable work. North, all IIT people, Professor Grija Jayaraman, Professor J.C. Mishraji, Professor Chetrani, several people did a lot of work in these areas. Now, in this porous media, I would like to present two people just for historical interest, highlighting the historical point of view of porous media here. Two people are prominent in one sense. I will come back in what sense they are very prominent. Fillinger is one person from Vienna, Austria. Terzaghi is another person. He is from Czech Republic. Both born in same year, just like our Hagen and Poisson, Fillinger and Terzaghi, both born in 1883. Of course, the month date are different. Fillinger is June 25, 1883. Terzaghi is October 3rd. Same year they born. And Fillinger lived for only 53 years, whereas Terzaghi lived for 80 years. Fillinger is a geotechnical famous engineer, and the Terzaghi also an engineer working in many areas, including civil engineering, geotechnical engineering, etc. And these two scientists did a lot of experimental work and also theoretical work in flow-through porous media. And their results are commendable. That is, this is the continuity equation. This is the momentum equation. Beta is the phases what we can have. Two types of phases we can have, fluid phase and solid phases. And V is the velocity here. T is the tensor, stress tensor. Pi is also the internal interactive force between constituents. We have the stress strain relations as given here. And the flow past a porous medium also very, very important. Recapitulating the standard Navier-Stokes equations. From the earlier equations, put phi f is equal to 1. That is solid fraction is not there, only fluid fraction is there. Phi s plus phi f equal to 1. Actually, if we put phi s equal to 0, automatically phi f becomes 1. The earlier equations will go back to the standard Navier-Stokes equations. Everybody knows q bar is the velocity vector, rho is the density, mu f is the fluid viscosity, P is the pressure, etc. So these are the Navier-Stokes equations. The matching conditions, continuity of velocities, continuity of shear stresses, jump continuities, etc. These are the matching conditions at the fluid porous mediums. In short, I would like to say that porous media work actually started by Voltman in 1794, further continued by Coulomb, Delichet, Fix, Darcy, Stephen, etc. They did good work. We know very well the experimental work of Darcy, which gave us the famous Darcy's law. Every student who is working in or every researcher in flow-through porous media knows the Darcy's law. This Darcy's law is nothing but Q bar equal to uh, K by mu, grad P, a simple one, F bar equal to 0 if I take. So the famous Darcy's law is known to us well. That is also an experimental innovation he made with different types of sands, water flows, etc. Darcy law is finally calculated. Q bar is equal to minus K by mu, grad P here. So that Darcy law is further generalized, say Brinkman model and a nonlinear models came into existence, flow through porous media got a lot of importance in explaining the different biological systems where the tissue layers are explained in those days. Professor Rudraya Garu, Dulal Pal, Professor Girija Jayaraman, J.C. Mishraji, several people worked, Professor Machi from IIT Madras, so many works one can see on these porous media theories. Many people have worked. All these works, what I say is that they belong to the undeformable porous media. These works are for undeformable porous media. But Terzaghi and Fillinger, they gave equations for both the things. And there was a quarrel between these two engineers, Fillinger and Terzaghi. That is, they led into a controversy in their publications. The thing is that the results published by Fillinger just prior to Terzaghi, of course, they were examined by a jury, a committee, as and the committee is about to announce the result the next day. Before that day, Fillinger got worried about his job, about his living, etc. And Mrs. Fillinger also shared all the scientific work with him. Both made grave decision to commit suicide in the night, March 7th, 1937. Fillinger and his wife committed suicide. Fillinger got afraid that his result will not be valid. That is the result he is going to get in the tomorrow's decision by the committee, academic committee. He feared the before day he got suicide along with wife, 1937. He lived 53 years only. But surprisingly, his results were said to be correct. There are also brilliant findings of Fillinger are there. And both Terzaghi and Fillinger made remarkable contributions to deformable porous media theory. So most of the works what we see are undeformable porous media theory. These two people did deformable porous media work in engineering, soil mechanics, relevant to the biomechanics also. So next question is Terzaghi. He is an influential person. He did prodigious distribution. He worked on soil, rocks, theories, capillary phenomena, design and construction of the earth, concrete dams, tunneling phenomenon, etc. The Terzaghi is famous for, he worked in Istanbul, the famous Massachusetts Institute of Technology, Harvard, and Berlin, Texas, Illinois, world famous institutions he worked, and he made enormous contribution to civil engineering world. He had a lot of students working all over the world. What happened is, therefore, his theory, that is the work proposed by the Terzaghi, became popular nowadays. Even though Fillinger's work is also equally good, but the theory proposed by Terzaghi on soil mechanics, that is deformable porous media, is now honored everywhere. So that is the thing happened regarding the two famous people, these Fillinger and Terzaghi. These people are famous for the deformable porous media. And just coming to the importance of this deformable porous media, there are many works. For example, Professor Vizurki sir from Dharwad did a lot of work in this knee joints or lubrication theory, etc. These theories will be confining to undeformable porous medias. So the attempts are still to be made in deformable porous media theory, because the cartilages what we see in the knee joints and several places, for example, the tissue layers in blood vessels, big blood vessels, arteries, microvessels, etc. These tissue layers have a lot of properties, and they can be more, it is more appropriate, I can say, to deal with the deformable porous media theory in many places. That is tissue layer mechanics or the synovial joint mechanics, etc. All these things, the theory of deformable porous media will be useful, and it is now being addressed by researchers all over the world. And regarding the biological fluids, there are many biological fluids starting from water, a lot of water in every human body, 70 kg, 40 liters will be there. For example, the sweat, cyst fluids, blood, cerebrospinal fluids, intraocular fluids, fluid in the eye. There are several fluids are there. A lot of research is necessary to know the dynamics of fluids in biological systems. And regarding the nutrients carried in the blood are released to tissues via the permeable endothelium of blood vessels. That is why Professor Rudraya garu did a lot of work in this area also. So endothelium mechanics, he proposed some slip conditions at the surface of the endothelium, etc. So one can do a lot of work in these areas. Peristalsis nowadays is not a new phenomenon. Just I would like to say that it is a well-known phenomenon which is known to us very, very long back. That is actually, it starts from, I can say, around 1969. Earlier also there were works, but a prominent work started from 1969 onwards. So with the works of the MIT professors, Professor Shapiro and his collaborators and his colleagues, they started this work here. And next MIT people, Professor James G. Brosier, 1985. These are the commendable works in this area. Nowadays, you can see a lot of papers. Every journal you can see the works on peristaltic transport, which describes the, you can see the figure, how the bolus transported, whatever we take, for example, the ice creams, that is foodstuffs, any foodstuff you take, how this is going. This is by only the peristalsis itself. So a wave is generated. How this wave is generated? This wave is generated actually, it goes back to the neuroscience actually. That is neuronal engineering, we can say. There we have the cable equation actually. That gives rise to different wave equations. And one of the waves or different waves are responsible in different biological systems for transporting the material, foodstuffs from the esophagus to several parts of the body or blood flow in the human body. So there are, nobody knows which wave is responsible for which flow. Which wave is responsible for ice cream flow, which wave is responsible for say some foodstuffs, bolus food, which wave is responsible for juices. So different waves are formed using the neurons. Neurons is a well-known concept for us. That is where we call it as panchendriyams. So that we know very well. So the touch comes from the one of the neuron. So like this, we can have different neurons are there. Ear, one neuron is there. Eye, one neuron is there. So that is neuronal modeling will take us to this peristaltic transport, in fact. So that gives rise to a wave. and that wave is like this, which is transporting the fluid. In general, simply we can say there will be contraction, expansion. In general, sometimes there may be only contraction, sometimes there may be only expansion also. So these are the muscle contractions which moves the bolus forward, that we know very well. There are other things, the intestines, peristalsis is there, heart peristalsis is there, chyme movement is there, several things are there, blood flow is there. These are the several things what we can have. Sanitary fluid transport, especially in the engineering design, industrial design, also we can have the finger pumps, roller pumps, etc. are there. So in this area, even our Sri Venkateswara University, Professor Vanatha Reddy is a student, Srinivas, worked on this experimental work in peristalsis also. He made good experiments to generate a peristaltic wave. So different rollers, which is not existing in literature, they did good experimental work on this area also. So it is attracting many people in Tamil Nadu also. Some universities are working in this area. So therefore, what I can say is that transport of corrosive fluids, etc., the peristaltic wave mechanism is very, very important. And everybody knows that. I was pointing out the usual fluid pumping, that is fluid transport from inlet of the pipe to the outlet of the pipe, that is from high pressure to low pressure. But here you see, the peristaltic wave can do anything. That is, I tell always the same example. I am able to take water, I am able to take coffee, I am able to take cold drink. At the esophagus, starting of esophagus, I have low pressure. But in the stomach, I have high pressure. I am able to take water, cold drinks, coffee, tea, everything from low pressure to high pressure. This pumping is made, this transport is made only because of this peristalsis only. So therefore, peristaltic wave phenomenon is a very, very important one in the living of the human beings or mammals in general. So therefore, no wave is still not established experimentally, which is the correct wave taking by the blood vessel or the stomach, any biological system. Mathematical modeling is taken place for the peristaltic waves, sinusoidal waves, trapezoidal waves, triangular waves, and SSD waves, etc. People are working with several waves and trying to see the fluid transport characteristics, that is pumping, that is streamline pattern, etc., which are useful for design of artificial things. That is, I was telling the earlier, the heart lung machine, blood pump machine, dialysis machine. In these biomedical applications, peristaltic mechanism is used very well by the biomedical engineers. So these are the industrial applications what we can have. Now, coming to the biofluids means there are several fluids which are not following the Newton's law of viscosity. That is, stress is proportional to rate of strain. That is the standard Newton's law of viscosity, I have to say. And it is followed by water and small gases like air, etc. But when I come to the gums, paste, jellies, or the cold drinks, etc., the usual Newton's law of viscosity is not sufficient. Therefore, people are going for different mathematical models. One can refer Kapoor textbook, the biology, that is biology in medicine. So mathematical modeling in biology and medicine. Lot of models they have discussed which are appropriate for the biofluid modeling. Carew fluids, Williamson fluids, Herschel-Berkeley fluids, power law fluids, hyperbolic tangent fluids, so many things, viscoelastic fluids. People are making several models are also. Not only that one, the wall properties are also examined by several researchers in the globe. Nearby, I can say Professor S. Srinivas, he is at present Amravati, Professor Radhakrishna garu, and his students, Marti Prasad, and so many people. Professor J.C. Mishraji, Professor Ramchandra Rao is the main person who did commendable work in this peristaltic transport initially also, he is one of the most prominent researcher in India who started work in 1995 itself. He did commendable work in this peristaltic transport. Actually, I am guided fluid dynamics by my revered teacher, who is no more now, late Professor Arunachalam Garu. But I got my teacher introduced Professor Ramchandra Rao Garu, and I learned all peristaltic transport only from Professor Ramchandra Rao Garu. Because of him, I am able to know something in peristaltic transport. So the work I have the opportunity to work with Professor Ramchandra Rao Garu. Some collaborative work also I have done with my student Subba Reddy also. And regarding the elasticity property, we know very well the peristaltic waves we were discussing earlier, different wave equations I was referring. When I want to send a wave on a pipe that is on the wall of the tube, I need the elasticity of the pipe. Elasticity is one of the important properties of the biological systems. That is why experimental work also available in the literature. Roshan Burton, Robinov and Keller, several people did some good works in this elasticity area. That is elasticity, modeling, elasticity mathematically, and also matching with experiments. That is the real work we can see in literature. All over the world, people are working with elasticity nowadays. And regarding the elasticity, elastic pipes, Newtonian fluid flows in a pipe. We have the different theories also. Rubinov-Keller theory and Young's theory is there. Majumdar theory is there. That is explaining elasticity. That is actually, you know very well, elastic material means stress-strain relation only. So the things are taken in different ways by, of course, they took the biological conduits also. So different modeling has been done. The explaining the elasticity of the biological vessel, blood vessel or any other biological conduit. So elasticity is one of the important things. As already said, the work in this area is also now you can see in several journals. One can see a lot of work here. Different fluids people are working here. So I have the opportunity to work with Professor Vajravelu, USA, and all my students worked in this area. And you can, Dr. Sreenivas from VIT Vellore, Hemadri Reddy Vellore, and so many people have worked. Devaki from SRM University now. So there are people who worked in this area. My students I am only referring. So their works I am going to present. One more thing what I would like to add is that, as already pointed out, Professor Shapiro is the starting person 1969 who did experimental and theoretical work in this peristaltic transport. Later, is it okay, visible? I mean, audible? Madam? Hello? Hello? Because the power problem is there, therefore I am worried. Okay. So the two-layer modeling is also very, very important in this area. Because you see, experimentally people reported that the saliva, etc., esophagus, there you can see one more fluid will be there. That is peripheral layer is also very, very important. That is actually pointed out by Professor J.B. Shukla of IIT Kanpur also. And later, Professor James G. Brossier gave commendable work for channel flows. Professor Ramchandra is the first person who gave for the pipe flow modeling with peristaltic waves for a Newtonian fluid with peripheral layers also. So, and followed by Professor J.C. Mishraji, Professor Vajravelu, and several workers have the opportunity to work on some of the areas also. Now, I would like to present, first of all, a model for, first I would like to give the model for deformable porous media and then come to the peristalsis. I would like to know, madam, what is the time I can stop? Based on that, I will Madam?
Sir, another 10 minutes, sir. Another 10 minutes.
10 minutes. Okay, madam. Okay, please. So just I will, with all this background, I am just presenting the models. One can do calculations very well. So coming to the deformable porous layer, let it be the articular cartilage, or let it be a what you can say, a tissue layer, endothelium layer in the blood vessel. So you can see this type of porous medium. This is different from the regular porous medium. Regular means you can see a lot of works. Overback convection extra, Professor Dre Garu, Professor Umavati Madam from Gulbarga, Professor Pratap Kumar, so many people, Professor Malshetti Garu, Shiv Kumar, Siddheshwar, so many people have done these areas. But this deformable porous media, I am presenting this one. So this is the deformable porous layer here. I have taken a simple non-Newtonian fluid. Actually, Jeffrey fluid contains two parameters. One is lambda 1, other is lambda 2. Only people are taking, for simplicity, only one model we are taking into account here. So this is a Jeffrey fluid model here. We have a vertical stratum. It is isothermal stratum here. That is the temperature same at the two walls, left wall and right wall here. And the flow takes place, you can see the arrow mark in the x direction here. And in this context, the governing equations are simplified. I have shown the equations of Terzaghi. Actually, we are following Terzaghi equations. Later, Bayet, Professor Girija Jayaraman Garu gave a good account of work in this area, and several other people are also there. And this is, you can see, the governing equation simplified version, just only 1 and 2 you can see. I am not writing the continuity equation. I have written the momentum equation here. First of all, here mu A is the apparent viscosity and V is the velocity of the fluid in the porous stratum, and K is the drag here. Phi F is the fraction, volume fraction here of the fluid. P is the pressure here, and beta is the thermal expansion coefficient here. T is the temperature of the fluid. T naught is the temperature of the surroundings, etc. So lambda 1 is the Jeffrey parameter. So this is a momentum equation which is derived from the laws of the Bayet or Barry, etc. And the second equation. So this is the difference between this usual, that is undeformable porous media and deformable porous media. Here you can see mu d square u by dy square minus phi s dou p by dou x plus kv equal to 0. See, this second equation u, it is the displacement of the solid displacement. The second equation is connected to displacement of the solid in the deformable porous medium. Here the difference is there. I think one can easily understand. In the usual porous medium, what happens is that the solid particles will not be displaced from the solid matrix. But in the deformable porous medium, the solid particles also displace. The fluid movement is there. So therefore, we have to take the governing equation for the solid displacement. That you can see, this is the second equation. Mu is the Lami's constant from elasticity. U is the solid displacement in x direction. Phi s is the volume fraction of the solid phase. K is the drag coefficient. V is the velocity of the fluid in the stratum. So this is the second equation which is important when you deal with the deformable porous media. And the energy equation is also standard conservation of energy, you know very well. T stands for temperature, and you can have this equation including the dissipation, etc. The boundary conditions are simple because I have taken a system, or I have taken a problem with rigid walls, bounded by rigid walls here. Definitely the no slip conditions are valid there, that is y equal to b, and t equal to t1 at the boundary. I have taken half channel because of the symmetry considerations, etc. Naturally, at the center line, the maximum velocity occurs, maximum temperature occurs, maximum displacement occurs. These are the assumptions we are putting forth, and that gives the boundary conditions prescribed for the problem, giving rise to these new equations. Here, I am not going to the details, and because this is a nonlinear problem, one can expand with the this is buoyancy parameter n here, and one can find out the solution, 0th order, first order, second order, etc. And these solutions can be made physically meaningful through the graphs also. So these are the 0th order system, just for example. Delta is the drag, eta is the coefficient of viscosity, etc. And validation is also made here with the undeformable porous layer work done by Rudraya garu, and the present work is for present work is the last one. Present work with lambda 1 equal to 0 means Newtonian fluid. Rudraya garu did for Newtonian fluid. Therefore, the comparisons are made with these works. That is the how the for example here skin friction changes at the wall y equal to 1 for different buoyancy parameters n. These things are made the clear how the deformable porous layer makes change over the undeformable porous layer at the boundaries. That is y equal to 1 is one boundary. Skin friction calculation, tau, that is tau ix is the shear stress at the boundary here. This is the comparisons here we can have here, and Jeffrey parameter variations are shown here with the skin friction parameters, etc. There are good conclusions one can say, that is the velocity decreases with the increasing delta, eta here, and also the displacement increases with increasing the Jeffrey parameter, drag parameter, etc. And the impact of buoyancy parameter is also seen in the skin friction also. And a good comparison is made for non-Newtonian Jeffrey fluids and Newtonian Jeffrey fluids, Newtonian fluids, and Nusselt number calculation is made. It is observed to increase with the Jeffrey parameter, etc. So this is the paper. Actually, it is published with my students in 2016. This is the work what we have made earlier. This work was with Kumaraswamy Naidu and other students. And I will go to a simple model. Quickly, I will go through the model because only 5 minutes are left out for me, 2-3 minutes here. I will quickly go through the things. Now here, we are going for elasticity property, deformable porous medium properties we have seen earlier. Now we are going for the elasticity properties. In that direction, just I will scan through, quickly go through this paper. That is, I have a model here. This is the physical model here, consisting of a core fluid and peripheral fluid. There is a pipe here. The pipe is external pressure is there, that is P naught here. You can have P1 at the inlet, P2 at the outlet. I can say the inlet pressure becomes, because P naught is non-zero, P1 minus P naught becomes inlet pressure, P2 minus P naught becomes outlet pressure here. There is a core region. That means one internal fluid is there, peripheral region is there, that is outer fluid is there. Two fluids are there. These two are having a common boundary. That is, you can call it as interface between these two fluids. I have taken the Jeffrey fluid in the core region, Newtonian fluid in the peripheral region. That is what we are telling. This is inner core region consists of Jeffrey fluid. Peripheral region consists of Newtonian fluid. So this is a good model for the explanation of the blood flows also. And we have taken the matching conditions, usual non-dimensionalization following Professor Ramchandra Rao works. And we found the fluxes Q1, Q2 here. Now we are introducing the elasticity property here with the works of Robinov and Keller and the Sochi and others, Roche and Burton. These elasticity properties are taken into account. Through the volume flux, we have introduced the elasticity property in the vessel, and then we have calculated the flux finding for the two-layer flow, that is internally Jeffrey flow, outer, that is peripheral, is Newtonian flow. We have calculated this Q, that is 27, you can see, that is the flux for this flow, amount of fluid got from the right end. And special case tallied with the experimental work, theoretical work of Robinov and Keller for a single fluid. That is the thing what I would like to emphasize. There are two fluids are there. Definitely there will be interface. The equations for interface are also found. Interface velocity is calculated. And there are several graphs for fluxes for different elasticity parameters T1, T2, Jeffrey parameter lambda 1, different inlet outlet radius, etc. And the work is validated with Vajravellu 2011 for a single Newtonian fluid and also with Robinov Keller. Good observation, or you can say good validation is observed here, and this appeared in May 2020. And next problem is, I am not going to explain. This is the same problem with the peristalsis property. Earlier problem is now, this is for a blood flow. Actually, any blood vessel need not have the peristaltic property. For example, arteries, they are with the big radius, etc. They will have less, very, very less peristaltic property. Or some Professor Lighthill, James Lighthill will say in his, there is no peristaltic property in big vessels like arterial blood flow, etc. But in micro vessels, definitely peristaltic property is there, micro blood vessels. So for such phenomenon, we have introduced this peristaltic wave here. Two fluids are there. The interface, core and peripheral layer, between them the interface is there. Inlet outlets are there. The peristaltic wave propagation is there. And we have introduced the elasticity, Robinov-Keller model here. And we have the results in this way. That is the flux results, streamline patterns, the interface equation, etc. And several graphs are plotted to explain the flux phenomenon, because flux is very, very important. Delta P, pressure gradient phenomenon, that is pressure rise is very, very important in peristaltic transport. And also the other things like shear stress, also we have calculated here. Velocities, interface velocity, importance of elasticity is also explained here. A good matching is observed by taking the experimental work, Robinov and Keller. Theoretical and experimental models are validated here, and we found good comparison between them for this Robinov and Keller work here also. And this recently appeared in this National Academy of Sciences very recently. So therefore, I have presented this one, and I need not say that this two fluid model results will go to Professor Ramchandra Rao in the absence of elasticity in 1995 Journal of Fluid Mechanics paper, and this will go to Robinov-Keller experimental and theoretical results also for a single fluid also. So these are the results which I would like to present. Good amount of work can be taken. All these works are presented and they are done with my students, Dr. Suneetha, Dr. A.N.S. and several students, Professor Vajravellu. All the people have contributed for all these findings. So I thank the organizing committee for giving me a good opportunity for me to share my few thoughts, whatever I could do with my students. Actually, with the students only we could do some work in research work here. So I think all people can work in these areas, and that may be a good one the nowadays here. Of course, I am not going to the further details. There are LDT and NDT things also. One can work in that area here. So linear density variations and non-linear density variations are also, they are also very good works nowadays in fluid dynamics, of course. Thank you very much for giving me this opportunity, to the Honorable Vice Chancellor Madam Garu, Registrar Garu, and all the faculty members, organizing committee, convener, Dr. Kathyayani, faculty members, Dr. Madhavi, Dr. Sreedhar, Dr. Suneetha, Dr. Sreenivasa Reddy, and all the friends in the YVU University. Thank you one and all. Thank you very much. Any
Thank you,
questions?
sir. Thank you, Srinath sir. Our Guru, mentor, whose presence and blessings are there whenever we sought his help. Thank you very much, sir. He correlated the fluid flow in humans, animals, with techniques and applications of theories and dynamics. Sir explained about the first basic problem, pipe flow, using the famous Hagen-Poisson law by Leonard Marie Poisson, Ludwig Hagen, and also the importance of Poisson law, and extended this law for more fluids like power law fluid, Herschel clay fluid, Casson fluid. He also mentioned about the prominent work of Paul Finger and Garaldi in porous media. Thank you, sir, for enlightening us and encouraging our students for the further research, progress of research in this area. Thank you, Srinath, sir.
1 minute, madam. This paper is, I have forgot to mention, with my guru, late Professor Arunachalam garu. This is the paper, last paper with him, Dr. Sumalata. So last paper which now Proceedings of National Academy recent appeared. This is the last paper which I could contribute with my guru. Wherever he is there, I think sir will bless me for this lecture also. Thank you very much, madam. Thank you, Dr. Madhavi. Thank you very much.
Thank you, sir. Thank you very much. Now we'll have some small tea break for 2 minutes, which is back by 12:05 here. Sir, we are giving some small break to our students.
Okay.
We will by 12:05, sir. Okay, sir? Kishan sir will proceed with his talk at 12:05.
Right.
Okay, sir. Thank you.
Thank you, madam. Thank you.
మనం ఇక్కడ రేట్ చేసి
Hello. Kitchen, sir. Hello. Kitchen, sir.
Sir, are you ready, sir? Yes, sir. Voice you not address. Unmute చేయండి sir. Unmute చేయండి. Sir, okay. Sridhar sir.
ఏం మేడం
Doctor.
కంప్లీట్ నుండి వాళ్ళు వస్తారు
Voice వినిపిస్తుందా?
లేదు.
Unmute చేసుకోండి. అదే అదే అదే
చేసుకుని వస్తాం
Unmute చేయండి. Sir, నమస్తే సార్.
హలో కిషన్ సార్ మీ వాయిస్ వినిపించట్లేదు సార్. హలో సార్ కిషన్ సార్ మీ వాయిస్ వినిపించట్లేదు.
ఇప్పుడు వినపడుతుందా మేడం?
ఇది బాగా వినిపిస్తుంది సార్.
ఓకే
ఓకే సార్.
రైట్ రైట్
స్టార్ట్ సార్.
ఓకే మేడం.
Okay, sir. Thank you, sir. Good afternoon, sir. I request my colleague, Dr.B.Sreenivasa Reddy Garu, to just brief about the profile of Professor M. Kishan, sir, from Osmania University. Now, I'll hand over the mic to Srinivasa Reddy, sir.
Good afternoon, sir.
గుడ్ ఆఫ్టర్నూన్.
It's a great pleasure for me to introduce our honorable resource person, Sir M. who is the head of the Department of Mathematics from Osmania University and the charge member secretary of Telangana State Eligibility Test. He had done his institutional services as Dean Faculty of Science, Mahatma Gandhi University, Telangana State, convener Common Busy Entrance Tests for 2019 year and 2020 year, Telangana State. Introduced the online exam to conduct the OUSET 2018 entrance exam in online mode, which is the first university in country for traditional courses such as MA, MCom, previously
etc. Director, DOA, Usmania University from the 22nd September 2017 to 6th July 2022. Chairperson, Board of Studies in Mathematics, Usmania University from September 2017 to October 2019. Chairperson, Board of Studies in Mathematics, Palmer University from 2019 to 2020. Coordinator, UGC, ESC LCP program, in Fluid Mechanics, Department of Mathematics, Usmania University. Served as warden for 2 years, from 2005 to 2007. Member, Board of Studies for PG, Autonomous Course at PG College of Science, Usmania University, Saifabad, Hyderabad. Joint Director, DOA, Usmania University from 31st October 2019 to 22nd September 2017. He attended 40 seminars and conferences. He has worked as a guide of MPhil and PhD research scholars. 20 research scholars got a PhD award and 6 research scholars got an MPhil award, and now presently working 8 members. He published over 60 papers in international journals and national journals. His projects are major research project PhD program, research project on study flow of incompressible non-Newtonian power law fluids, a numerical study. Coordinator is the DSCSR program in fluid mechanics. He registered membership into professional bodies like member Indian Science Congress, like member Andhra Pradesh Society for Mathematical Sciences, member Indian Academy of Mathematics. And as the resource person for the Part Training School for Junior Scientists at AMD and the Atomic Mineral Directorate, Begumpet, Hyderabad. Sir got State Best Teacher Award in 2020 from Government of Telangana. Thank you, sir. So start the program, sir.
Good morning, sir. Good morning. The voice is okay?
Yeah, yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
Good morning to all of you. Respected the Vice Chancellor of Yogi Vemana University, Professor M. Kalapati Garu, and the Registrar, Yogi Vemana University, Professor D. Vijay Raghavari Prasad Garu, and the principals, Chandramati Shankar Garu, and the convener, conference convener, Dr. G.Kathyayani Garu, and all other the faculty members, Madhavi Garu, and Dr. Sreedhar Babu Garu, and Dr.B.Sreenivasa Reddy Garu, and Dr. S. Suneetha Garu, and also the Professor Srinath Garu, the retired professor of Sir Namaste, retired professor of the SV University. The resource person to regularly to our Usmania University, also many conferences he has attended. He has motivated all the young research scholars, and the Yogi Vemana University, all the organizers, and this conference, I think, on the honor of in the superannuation of Professor T. Vasanthi Garu, this conference is conducting. It is a very good the conducting of this nature of when the one senior teacher is retiring, the department is conducting such a programs is a good practice. So on this occasion, I would like to take my talk on not purely on particularly the research problem. So just I will try to see that the young research scholars so understood the finite methods. Now I will try to see that how the computational fluid dynamics playing a important role in the fluid dynamics and other engineering the R&D developments. So whatever the development is there are all other defense or all other the transport or all other equipments, all any electronic equipments or whatever it may be, all must be depending on fluid dynamics, heat and mass transfer, the development on that. So for that, whatever the equations arising in that all will be occurred as a nonlinear equations. Therefore, to get a realistic problem, to solve a realistic problem, just now our Srinath sir is explained about the biofluids. So even though in the biofluids many the complex equations will be arises because of the geometry or because of the terms occurred in when the mathematical modeling. Mathematical modeling means what are the realistic problems is converted into the laws. Whatever the laws are converted into a equation that is called as a mathematical model. Ultimately, our job is to develop a mathematical model for a physical problem and solving a physical problem into a solution. And or many problems are not having a, or it is not possible to get a direct solutions. We have to go for some computational aspects, for which the CFDs plays a important role. So I think I am trying to see that there's some basics of finite element I can explain, so that some research scholars can go for instead of so many other methods, they can go for finite element methods or like find different methods also. So I will continue my talk on finite element methods, particularly on a fluid dynamics uh, problems. So 1 minute. The screen share is okay?
Yes, sir.
Yes.
Yes,
Okay.
yes, sir.
Now the finite element methods. 1 minute. The finite element analysis for heat and fluid flow problems. I have taken this topic, but basically I will go for the finite element method. How we can go for finite element method? Before that, what is the need of finite element methods? Just now I explained many problems in engineering which are arising as the either differential form or integral form. We know that either both the forms we can get an equations. Ultimately, the formulation of that we have to reduce into a set of algebraic equations or certain differential equations in a certain assumptions we will get. So ultimately, we need a solution for either it is exact form or closed form solution. We have to find out. So generally, when there is a complex geometries are there, or in the properties in the boundaries are complex, in the most real world problems are not having there is it is not possible to get an exact. We have to need a the find out a solution for in a reasonable amount of time. So and the so what is the need of computational methods or computational fluid dynamics we have been have? So many applications involves where the complex shapes are appeared or boundary conditions are complicated or material properties is their nonlinear properties. Then we can have the need of these computational aspects. And also there is a generally there is a gap between the solution of realistic problem and where there is no analytical solutions are existing and when we can have a applications when we want to find out a good solutions, there is a gap. It is not possible to get a analytical solution. We go for computational methods. And the computational methods, whatever the solutions methods we have, generally they find a different method, finite element method, finite value method, and boundary element methods, like so many other methods we have. And ultimately, by using any methods, finite different, finite element, finite value, or any methods, when we can have, generally we can use to discretize these methods, and we will get the approximate the solutions or approximation functions we will get for a differential equation. Generally, we will in a finite different method or for finite element method. So we will get ultimately the differential equations or whatever the equations are. Ultimately, we have to reduce into a system of equation, algebraical system of equation. Ultimately, that we have to solve. So mathematical aspects, what we will do, we can have in a fluid dynamics majorly we can have a law of conservation of mass, momentum, energy. Therefore, from which we will get it as a mathematical modeling that we can have equations, continuity equation, momentum equation, energy equation, and concentration equations. So which are non-linear and coupled in particularly in fluid mechanics. Therefore, it is not possible to get a analytical solution even though if some assumption is made. So it is not possible. It is a conversion to get a solution. So non-linearity, how the non-linearity will be the occurred, non-linearity will be in a physical problems, the will be in a different ways. So what are that non-linearities? May be due to the boundary condition, due to the geometry, due to the terms which are appearing in a equations. So we generally what we will do, we can make into a linearize the problem, and we have to solve by neglecting some terms or reducing the equation to non-linear to linear. So in a practical problems generally involves complicated geometries, complex boundary conditions, material properties, and coupling of the many equations. So one of which we are, I want to focus on finite element methods. So which are the finite element methods are well suited for such circumstances because they have the flexibility to handle arbitrary variation in boundaries and properties. Because whereas the finite different methods in a difficult geometry but curved geometries or in a complex geometry, it is not we will get a solution, but it is not get the accuracy solution, or it is not possible to cover the complete domain. So the finite element method will be shoot for that particular type of methods. Now coming to in a finite element method, what we will do generally in a finite element method, we have to which is in a computational scheme where the problems are occur like in another fluid mechanics or any other mechanics. So the finite element methods can be used in the finite element method. Whatever the problem or the physical problem we are taking, whatever the domain is there, that domain will be divided into number of subdomains, or we can call as a the body, whatever it may be, if it is a we divide into pieces, which we can call it as a subdomain. So each subdomain is here, we can call it as a elements. So for each element, what we will do, we have to obtain a approximation solution, or we can say that we can get it as an interpolation polynomial. So in a finite element methods, whatever the domain will be divided, and each domain is subdomain is called as element, which must be continuum and discretized into simple geometry shapes. The properties and the governing relations are assumed over these elements and expressed mathematically in terms of unknown values at specific points in the elements called nodes. So that means when we can have a nodes at each point, we have to find out the mathematical expression of each element, and whatever the unknowns are there, that unknowns we have to obtain from each element approximation functions, and for each approximation function of each element we can assemble it. So and after assembling whatever the system of equations in a we will get that we have to solve which will be provide a solution for a complete boundary value problem or initial value problem. So generally, what are the common types of elements we will get? A one-dimensional element, two-dimensional element, three-dimensional element. So in a one-dimensional element, what happened? The line element, like we can have this line element. So and two-dimensional means we can have a triangular elements and quadrilateral elements, and three-dimensional means we have a tetrahedral and rectangular prism elements. So in one dimension also, what we can take linear, non-linear, and first order, second order we will take. For example, one dimension line element means we will take first order here, it is a second order. That means here we can take a corner node size, nodes here we can take it as another node in the middle, we can take in a particular second order element. Similarly, triangular elements, if we can have like this, and we can take another nodal point in the mid one, we can have similarly quadrilateral, hexa, and tetrahedral. We can take the first order or second order or linear column. Now, the discretization of the problem means how we can take, for example, I am showing the example of plane or two-dimensional area. So where we have to divide the each domain into triangular elements. Now let us say that when you can divide, each may be equal or maybe a different size, we can divide depending on the problem. So if we can divide the domain into like this, or you can divide into more number of elements, it will be becoming like this. For example, here 228 elements, here 912 elements. So depend upon the domain dividing number of elements increases, the error will be reduces. Now ultimately, what is the 4 or 5 steps we can here have? One is divided into the element, domain is divided into the element. Each element we have to find out the polynomial equation, and after obtaining the polynomial equation of each element, we have to assemble it. And after assembling, what we will do, we have to impose the boundary condition. Then we can have a system of equation. Then we can solve it. So there are two ways, or we can say that two approaches we have in a finite element methods. One is weighted residual method, another one is a variational methods. So what we will do in a weighted residual methods? Weighted residual methods are methods which provide approximation solution to the differential equation, which of the either it is a boundary value problem or initial value problem. So what we will do when we can take a boundary value problem or initial value problem, whatever the differential equations are there, which will provide a algebraical approximation function, it will be provided. So let the boundary value problem, let us say that this is a boundary value problem where L is a capital L means it is a denotes the differential operator. V will be the appropriate boundary conditions. So here L may be a second order, third order, fourth order, whatever it may be the order of differential equation. So in general, it is defined as within the particular domain, and it is on the boundary of a domain. The boundary conditions are given. Where X means here it is not single variable. It may be a number of X1, X2, X3, so on like that. Number of variables we can have. So when we can say that this is a boundary value problem, so naturally there will be a solution will be existing. So when the solution will be existing, let us assuming that there is a solution, approximation solution. So let us say that we have to obtain for solution for u. So for u there is a solution, approximation solution. Let us assuming in a such a way that how we can assuming the approximation function small w is x comma into a1, a2, a3, so on like that. A1 means these are arbitrary parameters. So depending on the differential order, we can choose this approximation function. So when we are assuming approximation function, so therefore this approximation function, when you are substituting in a differential equation, it must be satisfied. So that means what it means, you are assuming a solution for this differential equation or boundary value problem. So it must be satisfying this boundary value problem. Then only we can say that it is a solution. So then what we can substitute in this, but what we can take it as a, which is not exactly the solution we are getting, we are chosen as approximation solution, therefore which is not equivalent to 0. So therefore there may be a, when you can substitute to the approximation function into a differential equation, there may be error, or you may submit to the in the boundary condition, there may be error. The error may be occurred in a differential equation and boundary in both boundary conditions, or maybe only in differential equation or in a boundary conditions. Let us say that the approximation function is satisfied, not satisfy the boundary condition, they satisfy the differential equation. That means instead of u, you can substitute the approximation function which is satisfied in the domain, but it is not satisfied on the boundary. Therefore the error will be occurred. That error will be, let us say that ei, because the number of boundary condition, therefore number of errors will be occurred. Depending on the each boundary condition we have error, therefore we say that which is biw and minus GIF is not equivalent 0. Here you can say that when you can substitute here u, VIW must be equivalent GIX, but there is an error, therefore it is not equivalent 0. Therefore such methods we can call it as a boundary method. That means boundary method means in the at the boundary the approximation function is not exactly, therefore there is error occurred, that is called as a boundary method. Similarly, if it is when you can substitute or when you can take in a different boundary value problem where u instead of u, when you can substitute w, and which is not satisfy the equation, there is an error, therefore that error you can take it as a capital E, that or you can say that within the domain there is a residue, therefore you can say that LW minus fx which is not equivalent 0, that quantity is an error, that is you can call it as a E. E is an error which is occurred in a interior domain, inside domain, therefore we can call it as also called as a domain method or interior method, but it is satisfied on the boundaries. This the approximation function is satisfied on the boundaries, therefore it is a we can call it as a the domain method. So sometimes what happen, neither satisfy the within the domain nor satisfy the on the boundary, the approximation function we can call it as a mixed method. Now what is ultimately, what is that we want to see, that we want to get a fruitful solution, or which must be the exactly to the differential, the boundary value problem. When we want to solve the problem, which must be reflect means whatever the approximation function is there, that must be equivalent to the exact solution. Therefore, what we have to see that the error must be tends to 0. But the error, or we can call it as a residue in the equation, differential equation must be tends to 0. Therefore, if it is not possible to make it to 0, but is tried to see that it must be identically 0, not exactly 0, it must be see that identically 0. So therefore, in the error distributing methods, the error whatever it may be, E x comma a, here a x comma a means x may be x1, x2, x3, or if it is in two variables x comma y, whatever it may be. Similarly, the parameter depending on that a1, a2, a3, so on like. So approximate to the 0 so that we can take a weighted averages. Now the orthogonally we can say that this error must be residue function must be tends to 0. Therefore, we can take with the weighted averages, that weighted average with respect to this weighted averages, this integral of over the domain, that we can take it as an orthogonal function of integral of over the domain. The residue function and weighted function must be equivalent 0, where we can say that this Wj is called as a weighted function. So weighted functions, depending on the functions, we can have a j is equal to 1 to m, that means w1, w3, so on like that. Therefore, which with respect to the weighted function, that residue must be over the domain must be tends to 0 or equal to 0. We have to see that this actually whenever we can solve this, depending on j is equal to 1 to m, so we will get actually the number of if j is 1, you will get one equation, j is 2, you will get another equation. Therefore, you will get it as a number of nonlinear algebraic equation we will get. If m means we will get depending on a1, a2, a3, so on am, we will get m linear nonlinear equation. So this approach is called as a weighted residual methods. That means where we can take with respect to the weighted functions. So the residue is equating to 0, then we can call it as a weighted residual methods. So depending on weight function, the weighted residual methods we have many different methods we have. So let us say that least square method. So least square method means here you can see that everywhere residue is there e of x a, e of x a, e of a. But here in the least square method we will have a weighted function is dou e by dou aj. Dou e by dou aj means e is a residue function, and with respect to residue function, wherever the with respect to the arbitrary parameters, if the residue function is taken a derivative, that weighted function is defined w as dou e by dou aj, which is called as the least square method. Going to the Galerkin method, wj, capital wj is a small wj is in a small w is an approximation, capital w is in a weighted residual method. If we can take here, wj is a dou w by dou aj. That means approximation function with respect to the arbitrary parameters, when we can take it as a weighted function, which will call as a Galerkin method. Similarly, collocation methods, when the collocation points where it will be defined, we can take the del of x minus xj. So then we can take it as a collocation method. Similarly, momentum method means that chosen particular polynomial function for j is equal to p of g of x is equal to x power j. That means j is 0 means you will get 1, j is 1 means you will get x, so on like that. When you can take polynomial function, which will becoming as a momentum method. Similarly, partition method means instead of r, you can take it as a number of subdomains. Each subdomain it is defined, in other subdomains it is not defined, which will become 0, therefore which is called like this. Coming to the variational methods, in the variational method, what we will take, we can take a functional. We know that what is a functional. So the variation of functional will be equivalent to 0. Therefore, in the variation of function, when we can take this f. So here we have taken as the functional. This f is a only first order derivative taken, the x u dash. So we know that what is the Euler's function for this f. Therefore, when it is satisfy the when we can take a function in a such a way that which satisfy the Euler's equation, that f we can take it here. So we can the variation of that is the functional is equivalent to made into 0, del j equivalent to 0. Therefore, we can call it as this approach is called as a variation method. That means what we are doing, it is a functional we can take variation of that functional is equivalent 0. Whatever f is there, that f is nothing but f x u dash. Which f here we can take? That which f means this inside function, whatever it may be equation, that equation must be satisfy the Euler's equation of form. That means what is Euler's equation of form? So my minus d by dx dou f by dou a dash plus dou f by dou w is equivalent 0. So if it is satisfy that, then that f we can take here. That f here we can take. So then we can get that method is called as a variation method. So going to the ultimately what is the type of errors here we can get? It is how the accuracy we will get in the convergency in a finite element method. So what we will do, the approximation we will get it depending on the approximation function for each element. So when we are taking the approximation function, naturally, so depending on arbitrary parameters, we will have a order of polynomial function we will get. If it is in a less number of order of polynomial function, if we can take, the error will be more. Therefore, depending on approximation function, the convergency or accuracy will be depending on, and number of elements, how many number of elements you are dividing. So if it is a smaller element, you will get more convergency or more accuracy, and the lesser the elements when you are dividing. That means the more number of elements, subdomains you are dividing, means the number of element size will be less. So and when you are integrating, numerical integrating errors also will be occurred. So the computational errors means we can have a round of errors. Therefore, how many type of errors we will get because of when you have a domain how we are approximating, and interpolation of each elemental equation, and when you can take integrations, and when you can go for a numerical computational error, these errors will be occurred in a finite element approach. So when you can get it as an accuracy is nothing but error we will get, that is an exact solution minus finite element solution. Absolute value will nothing but a error. So the convergency, when we will get convergency we can have two types of convergence. One is number of elements. So that means when you can, depending you are dividing more number, then you will get a convergence. That convergence is called a H convergence. And if you can take more order of polynomial function, so that you can take it as a or approximation function, we can call it as a P convergence. So generally error tends to be 0. Residue must be 0 means as number of elements of approximation order it tends to infinity, then the error will be tends to 0. Now going to, let us go for one dimensional elements, how we can take. So that are the methods we are using in the finite element methods. But so before that, to get a elemental equations, how we get a elemental equation, let us discuss first one dimensional equations, for example. So let us take one dimension means I am going to take line element. Line element means, for example, there is a the interval or the length from A to B. So A to B we can have the this what we are doing. Let us divide into number of sub intervals. So sub intervals means you can, each sub interval is called as the element. Therefore here A is nothing but let us say that you can take x0 to x1 one element, x1 to x2 element, so on like that, xi minus 2 xi, xi to xi plus 1, so on like that. So up to xn plus 1, because the n plus 1 nodal points are there, and we can have a n plus 1 elements. So here the typical element, general element, instead of I, j or something n, because we are all using all other things, so we can denote it as a element E. That means we can say that it is a typical element E, let us say that. Now how we can find out the linear Lagrange polynomial for this particular typical element? So each element we have to find out a linear Lagrange polynomial. So let us say that I want to take it as this the interval xi to xi plus 1. So how we can find out xi to xi plus 1? Let us say that this is a typical element, general element. So we want to find out the approximation function, polynomial function. So linear Lagrange polynomial. Linear Lagrange polynomial means we are not taking any midpoint in this. Therefore, we can have linear Lagrange polynomial. Therefore, we know that from Lagrange polynomial, simply what is that here unknown? Unknown is an u. U means complete x0 to a to b, which is the whatever we want to describe, that is u, unknown function, which is a function of x, which is a one dimensional. Therefore, to find out that, but we are taking xi to xi plus 1 means The UE is for this typical element, there is this particular interval, therefore we are denoting a U of E, means this U of E is for this particular typical element. Therefore, as per Lagrangian polynomial xi plus 1 minus x2, xi plus 1 minus xi, ui, where the function at xi is nothing but the ui, the unknown function is at xi plus 1 is ui plus 1. There, x minus xi by xi plus 1 is xi, ui plus 1, this is a Lagrange polynomial we know. So we will take this as this ui coefficient will be taken as a this we can denote it as a ni. This is denoted as a ni plus 1. Therefore, this ni and ni plus 1 will be called it as a shape functions. So this u of e is nothing but we can write it as a ni ui plus ni plus 1 ui plus 1 where ni is defined as, or we can take it as a shape function, ni plus 1 is taken as a shape function. Similarly, for two-dimensional element, for example, two-dimensional element means, so we have a two-dimensional element means triangular elements, and here also in the line element also we can go for quadratical. So here is the xi to xi plus 1, you can take midpoint xi plus 2, then again you can write it as a Lagrangian polynomial. There you can take it as a xi plus half and ui plus half, three terms you will have, and ni plus half, ni plus 1 you will get. As per that you can find out, but there is no time, just I want to go for only linear Lagrange polynomials to understood the methods. Even though two-dimensional, simply linear triangular element I am taking. Many rectangular elements are there, other elements are there, but only I am considering the linear triangular element. If it is a quadratic triangular element means you have to take midpoints. Again, the 4, 5, 6 nodal point you have to take. Therefore, x4, y4, x5, y5, and x6, y6 like that. But here only at the corners, at the edges, we are taking the nodes. Let us say that it is a typical element. That means it is wherever we have divided the above domain into number of subdomains here. So here in the first we have shown here not for all the elements. For example, typical element, only general element I am taking. For general element, how we can get it as a polynomial function that we have to see for triangular element. So when we can take this, the nodal points we can have this. Now we can write it as a the nodes, and we can assuming here the approximation function for this triangular elements. Naturally, how we can assuming? We can assuming this as a the shape function of at nodal point 1, u1 it has nodal point is a described function will be at nodal point 1, and here it nodal point 2, that is the u2, here nodal point 3, that is u3. Therefore, u of e of this particular element approximation function is nothing but shape function n1 u1 plus n2 u2 plus n3 u3. So we want to find out actually in the line element by using the Lagrange polynomial we obtained, but here it is not, we will take in a triangular element, it is not by the Lagrangian polynomial. It is therefore we can assuming in a such a way, and we can go for the approximation function. We can take it as an like a plus bx plus cy, because it is a two-dimensional, two variables are there. So arbitrary parameter a only constant, and some parameter with x coefficient, some parameter with y coefficient. Therefore, we can assuming in a form of a plus bx plus cy. Therefore, when you can substitute a, b, c, and you can find out a, b, c, you can substitute here. We will get a shape functions n1, n2, n3, and then the three equation approximation equation we can estimate here. So this elemental u of e is a polynomial function, or we want to get a function, approximation function for this typical element. Therefore, which can be, we have assumed, or we have taken a plus bx plus cy. So therefore, which can be written as 1 xy matrix, in matrix form we are taking. When you can multiply again, you will get equation 4. Now here, so this is for typical element. This expression, this equation 4 is for expression for typical, complete typical element, triangular element. Now I want to take this expression for at nodal point 1. That means at nodal point 1 means u will be coming as a u1. u1 means here it is x will be coming as x1, y will be coming as y1. At nodal point 2 means u will be coming as a u2, and x will be coming as x2, y will be coming as a y2, and like that here we can have a x3. Therefore here we can have a u1 means from this equation 4, u1 means a plus bx1 plus cy1. Similarly, a plus bx2 plus cy2. Similarly, a plus bx plus cy3 for u3. So we can write this equation. This has a U equivalent to column matrix. You can write this in a matrix form. 6, 7, 8 we are writing in a matrix form. This U equivalent to column matrix as U1, U2, U3, and this A is means 1 x1 y1, 1 x2 y3, 1 x3 y3, and A means it is a column matrix of ABC. So this can be written as in a matrix form as a matrix of U is equal to matrix of A equivalent to A. That means here U1, U2, U3, and this we will have. That means 6, 7, 8 can be written as a equation 10. So 6, 7, 8 can be written as equation 10. Then you can find out from which ABC you can find out. Here ABC you can find out and substitute here. Substitute in the above equation, 5 equation. Then we will get to the, and compare with this with the U1 multiplication, U2 multiplication, U3 multiplication, that are nothing but the shape functions N1, N2, N3. So then when you can to obtain this, what we will do, this is, let us say that this is A you can push this side. So therefore first we can find out the matrix what is A inverse. A inverse means this determinant of 1 by determinant of this, and this you can take simplify this. A inverse you will get in as equation 12. So where del E is equivalent to area of the triangle of area of the triangle. So therefore when you can take it as a inverse, therefore we can have a ultimately from this equation I want to know, find out ABC values which are arbitrary parameter values, therefore which is equivalent to this when you have taken this is A, therefore A inverse of U1, U2, U3. So therefore ABC equivalent to A inverse of U1, U2, U3. So ultimately this you can substitute here in the equation ABC. We know ABC, therefore UE is nothing but 1xy into ABC. What is ABC here? A inverse into U1, U2, U3. So therefore from that equation 5 we have a U of E is 1xy A inverse U1, U2, U3. So we know that what is A inverse from equation 12. You can substitute here A inverse. Therefore so when we can have A inverse is this is nothing but A inverse. So and U1, U2, U3. So when you can cross multiply 1xy, you can multiply this, you can multiply, you will get this equation. So again you can U of E is nothing but when you can compare this equation, when you compare this U of E equation, so here U of E is nothing but N1 U1 plus N2 U3 plus N3 U3. Therefore if we can take here left hand side is equal to N1 the year, so N1, N2, N3, if so on like that. The right hand side you can get it as a 1 by 2 del E, 1 by 2 del E, and the when you can multiply this, so then what happened? X2 y3 minus x3 y2 plus x y2 minus y3 plus y x3 minus x2 into u1 plus so on like that we will get. So u1 coefficient, what is u1 coefficient here? U1 coefficient is nothing but we are writing it as a n1. So u1 coefficient is nothing but n1, therefore we can write it as a 1 by 2 del E. That complete A1 we are assuming as a this for our convenient, what we are assuming, this x2 y3 minus x3 y2 as a A1, y2 minus y3 as a b1, x3 minus x2 as a c1, and similarly x3 y1 minus x1 y3 is as a a2, and y3 minus y1 as a b2, x1 minus x3 as a c2. Similarly x1 y2 minus x2 y1 as a a3, this is b3, this is c3. Therefore we can write it as that coefficient. U1 coefficient is nothing but this means a1 plus x into b plus y into c, c1. Similarly we can write that the n1 is nothing but in the equation 16, n1 is nothing but 1 by 2 del E a1 plus b1 x plus c1 y, where a1, a2, a3, b1, b2, b3 is defined, or from we can assuming like that. So here our convent, what we will do here, so here is a linear triangular element n1, n2, n3s are there. So when we n1, n2, n3s are there, the shape function NE, the NE means the shape function for a particular typical element which are having a n1, n2, n3. Therefore we can write it as a n1, n2, n3. What are the pi of A unknown parameters? The pi of A at the concerned the respective nodal points U1, U2, U3, which are we can take it as a column matrix. So this 16 can be written like this. 16 can be when you NE pi E, if we can write like this, the 16 can be written as N1, N2, N3 into column matrix U1, U2, U3, which is nothing but 16. Therefore in a matrix form we can write like this. So when we can go for So one example I want to take for one-dimensional problem by using, we are not going all methods, we are not going all type of elements, we are not going all type of polynomials because the timing is constrained. Just I want to explain one problem simply, then if we can, anybody follows, they can try for our fluid dynamics problems. So let us simple problem which are in a particular textbook I have taken. So this is a second order ordinary differential equation. So and here we want to find out the variational methods. So ridge variational methods. Here we have to see that instead of this we can take it as a functional like this. So instead of this we are taking as a g of u is nothing but f of x comma u dash. So how we can get this function x comma u dash means, so this f when you can take into a Euler's equation of form dou f by dou u minus df by dx of dou f by dou u dash, then you will get this differential equation. So which f is satisfy the, or which differential equation is satisfy the Euler's equation of form, that f we can take inside the functional. That is a variation method. So therefore here we have taken, so where let us assuming approximation function, ultimately what we will take approximation function here, it is a one dimensional, therefore line element we can take. Line element is from let us say that xj to xk, the line element it is a domain from xj to xk. Therefore the xj to xk interval, that let us say that element, typical element, the typical element length can be assumed or denoted it as L of E. L of E minus E is nothing but xk minus xj, the length of a typical element. Therefore when we can take it as we have taken a linear Lagrange polynomial. What if we can take it as a linear Lagrange polynomial? Nj is nothing but n of j is nothing but nj xk minus x by xk minus xj. Xk minus xj is Le. Similarly, x minus xj by xk minus xj, therefore L of E. Therefore which we can express the here like this, and then these are called as the safe function for this. So ultimately we can take the variation of this function is nothing but equivalent to 0. So when we can get it as equivalent to 0, ultimately we will get it as the summation of number of elements. Therefore a of e pi of e minus b of e we get. So here we can see that each element we have taken a n of e pi of e. Like that we can also have each element. Here also we will get a of e for each element. Pi of e means particular typical element. What is the pi of e here? Uj uk column matrix is nothing but pi of e. So here the VE means whatever the matrix you can have the known because of the boundary conditions, known conditions, we can get that is a V of E. So now coming to this, now ultimately what is the functional we can have? We can take the domain. This is a functional for complete domain. Complete domain is here plus or minus 1 is 0. That is minus 1 to 1. Therefore complete domain is minus 1 to 1. Therefore, but we are dividing minus 1 to 1 into a number of subdomains, maybe a number of 100, 200, 300, 1000, whatever it may be. So let us divide that domain into number of subdomains. Therefore, let us say that particular subdomain is Rj. So Rj means we can have a functional for this particular typical element. Therefore, that particular typical element xj to xk element functional is called as a j of e. So the total functional is nothing but summation of all the element functional, where j of e means here you can take instead of u, you can take it as a particular typical element function, that is ue, therefore which will becoming as a this functional for a typical element. This is a functional for complete boundary value problem. So therefore ultimately variation of a functional of a complete problem is nothing but summation of a functional of variation of each elemental equation. Therefore ultimately what we will do, we have to take the variational for a particular typical element, and summing of all we will get a system of algebraical equation. For how we can get it, let us say that functional of a particular typical element. Therefore what is the optimal condition for that? The variation of del j is 0. The del j means what happened with respect to the arbiter parameter, the nodal quantities. What are the nodal quantities is pi e. Pi e means here uj and uk, because only two nodes are there. Let us say that it is uj uk. Therefore with respect to uj, with respect to uk. So where there we have discussed A1, A2, A3, so on like that. What are the arbitrary parameters? But here the U1, U2, U3 are in a other form of the nodal quantities, where in a particular nodal point we have to find out. Therefore, here in a line element, therefore only two nodes are there, linear Lagrange polynomial, therefore Uj, Uk. So with respect to Uj and with respect to Uk, you can take. So ultimately, what is this phi means, which must be equivalent 0? Let us say that with respect to Ue. Uj, with respect to Uj means what happened? U of E is nothing but, here you can say that U of E is nothing but nothing but here Ne pi E. Ne pi E means if we can take dou U by dou J, dou U by dou Uj, dou U by dou Uj means what happened with respect to Uj means you will get to only Nj, and dou U by dou Uk means you will get only Nk. Similarly, if I want to U dash, what is U dash? U dash is nothing but, because U dash means du by dx only one variable. Therefore, Uj, Uk are not function of x, but Nj, Nk are the function of x. Therefore, what you will get here, U dash E means Nj dash Uj plus Nk dash Uk you will get. So, dou U dash by dou x, dou U dash by dou Uj means you will get Nj dash, and similarly you will get Nk dash with respect to Uk. So therefore, so here when we can get it as this, so when you can take this with respect to Uj, then what you will get, so when you can substitute that that means U dash E means we can substitute U dash E is nothing but Ne pi E whole square. That means Ne pi E means Nj Uj plus U dash means here you will get Nj dash Uj plus Nk dash Uk whole square. So therefore, ultimately what happened? So Nj dash Nk dash Nj dash Uj plus Nk dash Uk. That means we can write it as a matrix form. Nj dash Nk dash Uj Uk means pi E whole square. Whole square means you can take twice of that, where this twice into half, and you can differentiate this twice into half, that vanishes. Therefore, what you will get, Nj dash Nk dash pi of U will get, pi of U. Then, and inside differentiation you will get. Inside means dou U dash by dou Uj means you will get Nj dash. So this is Nj dash we will have. So Nj dash that we will have. Now coming to the next term, 1 plus x square dou U square. Dou U square means here you can take it as a Nj, Nk and Uj, Uk calorimetric whole square. Therefore, when you can differentiate with respect to Uj, twice of that means twice this vanishes. You will get Nj, Nk, Uj, pi of E means Uj, Uk we will get. So therefore, we can have that, and inside you can take with respect to Uj, you will get Nj. Sorry, here actually this is only Nj. This is only Nj, not both. And similarly, you can take 2 of E. 2 of E means here Nj and Nk. That means with respect to Nj Uj plus Nk Uk means with respect to Uj means you will get only Nj. Similarly, with respect to Uk, you will get this. So both equations we have. So now we want to combine with these both equations. We can write it as a dou U by dou pi I. Dou pi I means here Uj Uk. Therefore, xj to xk, this nj dash here, nk dash here, you can write it as a column matrix, and whatever this inside which is same, and pi of E means pi of E, and here nj is there, here nk is there, nj, nk, dx is 0. So therefore, we can have the equations we can have. Therefore, when you can take this cross multiply here, you will get xj to xk, nj dash, nj dash, nj dash, nk dash, nk dash, nj dash, nk dash, nk dash, 1 plus x square, so on like that. When you can take, we can take into the multiply, we will get it as a 2 cross 2 matrix here. So ultimately, we have to simplify this, or this we can write it as a n transpose. From this we can write it as a, this is a n dash transpose, and this is n dash. So that equations we are writing into form. Anyway, this equation we can, from which what we can take integration of the matrix, we can take it as a matrix of integration. We can exchange the commutative property. We can take integral of matrix is nothing but, now we can take matrix inside the matrix, we can push the integration. Therefore, after that, whatever we will get, that we can take simplification, we will take it as a this a of E, whatever we will get with of pi E. So whatever we will get integration of that, we can take it as a of E and pi E. Therefore, this is known. Therefore, ultimately that we can take it as a of E means ultimately this So integration inside you can push, that means integral of nj dash dx, nj dash nk dash dx, so on like that. Similarly here also 1 plus x square. So similarly we can take this simplification. So we know that what is nj dash? Nj dash is nothing but x minus xk minus nj dash, here we can take it. What is nj here? So here nj is xk minus x. What is nj dash? Minus 1 by le. Similarly nk dash is 1 by le. So that you can substitute here. So then we will get it as a so here you can nj dash means minus 1 by le, nk dash is 1 by le. For example, we want to evaluate all the things, you can substitute nj dash means minus 1 by le, minus 1 by le, which will becoming as a 1 by le square. When by 1 by le square is you can taken out, then you, the xj to xk dx integration means x limits of xk minus to xj, and xk minus xj length is nothing but le by le square. Therefore ultimately again we will get minus 1 by le. So similarly nj dash nk dash, when you can simplify, we will get minus 1 by le, otherwise we will get here 1 by lb, so on like that. You can simplify all. I am not showing here, we can simplify all here. Here you will get minus 1 by le here minus 1 by le, here minus 1 by le, here you will get 1 by le. Similarly, so on like that, when you can substitute here, we will get it as a simplification. Minus the AE matrix will becoming as a minus 1 by le, 1 minus 1 minus 1 1, and le by 6 2 2 2 2 to 6 plus. And when you can simplify this, because here it is a 1 plus x square, the x terms are there. When you can integrate it, you can into certain simplification, you can get into a particular form. So this is again little bit a complicated exercise we have to do, but I am not I'm skipping here, just we will take here. So again we know that what is le is nothing but xk minus xj, the length of element we have. So this is a and be means the right hand side, whatever we can have the right hand side, that the only nj nk. So whatever the nj nk, this nj nk integral, we can take it as the integration of matrix of integration of nj dx nk dx, that is nothing but b of e. You can simplify b of e, we will get it as a b is nothing but integral of nj. So and when you can simplify this, we will get b is equal to le by 2 1 1. So ultimately what is our job? We have to take the functional. For functional variation we have to take, and what that for that we have taken. For here we got it as a of e pi of e minus b of e, we got for a typical element. So therefore what we will do, it is not possible to many equations. We will generalize the standardize the element, each element, and for standardized element we are getting for the approximation function, that is nothing but a of e pi of e minus b of e. So let us say that there n elements are there, you can assemble for all the n elements, you will get that approximation function. For in a such case, let us say that there are two subdomains are there. For example, so I have taken minus 1 to 1, in that minus 1 to 0 1 element, 0 to 1 another element. Let us say that here the element 1, let us denote it here as at minus 1, the unknown function is u1, at 0 that is u2, at 1 that is u3. I am denoting the unknown the nodal quantities u1 u2 u3. u1 is at minus 1, u2 is at 0, u3 is 1. So this is element 1, this is element 2, let us say that. So what is element 1? The element 1 is, let us say that is here xj, here x1, xk. So here xj means minus 1, xk is 0, length of element is 1. So now you can substitute when you know the xj and xk. So and length of element, that is 1, you will get it as a a1. So when you can substitute there, the a1 is nothing but there, from which when you can substitute, you will get it as a this so and so. B of e is also, you can get b of e is le by 2 1 1. Therefore le is 1. Therefore we will get it as a of 1 1. So you can go for element 2. Element 2 means xj is 0 and xk is 1. Therefore le is 1 again. You can simplify, you will get this equation. Now we want to solve for complete domain. Therefore we have to assemble this both elemental equation. So when we want to assemble this both element a1 plus a2, therefore you can take a1 plus a2, but this is representing this 2 cross, these are all completely not 2 cross 2, 2 cross 2 both, we cannot combine, we cannot take it as a 2 plus 2 matrix. So because this is a coefficients for u1 and u2 representing, this is for another element, that is a u2 u3. So therefore, we can combine this in a such a way, the corresponding, that means here if you can write it for three matrices U1, U2, U3, so third column, third row is 0, and similarly the third column is third element is 0 here. Similarly here you can take for U1, U2, U3, but U1 is not here. U1 you can take first column, first row is 0, and U2, U3 similarly here first you can take it as a 0, and you can combine this, then you will get a particular form. Here there 1 plus 1 and the right hand side U1, U2, U3 for 3 cross 3 you can write, you can sum it, you can get it. Now you can, here you can incorporate the boundary condition. What are the boundary conditions? The U minus 1 is 0 and U1 is 0. One means at the both the entries it is 0. Therefore you can incorporate the unknown function is only U2. So when you can incorporate to in this, you will get U2 is so and so. So when you can the other problems, when you can divide it into 100 elements, 200 elements, 300 elements, like you can get it as ultimately you can get it as a system of equation. So assembling all the equations, then we can get at a solution. Now, for example, similarly, you can go for 4 elements. So the xj minus xk is for first element is -1, and the -1 to -half, -1 to 0, -half to 0, 0 to half, half to 1. So again, you can substitute all xj, xk values in the above equations. So where a of e, then here you can simplify, and you will get 4 elements a1, a2, a3, and you can combining all depending on this is for u1, u2, this is u2, u3, this is u3, u4, this is u4, u5 last. So you can simplify and you can combine, we will get this equation like this. For example, here only u1, the at -1, here you can see that at -1 it is 0, at 1 it is 0. That means at 1 means here we have denoted it at 1, that is u5, therefore u5 is 0, here it is u1 is 0. So therefore, if the both are not like earlier problem, u2, u3 is 0. Here it is an at 1, that is nodal is denoted it as a u5. Therefore, u5 is 0. When you can incorporate the boundary condition, then you can simplify, you will get a solution. So like our the E-time mass transfer problems or E-transfer problems, we can have a standard one equation. So that is a Faulkner scan equation we can have. So that is this standard equation, f double dash plus ff double dash plus beta 1 minus fd square, how we will get here. So the conditions are f0 is 0, f dash 0 is 0, f dash infinity is 1. Now here the third equation means if we can assuming a linear Lagrange polynomial, then what happened? For example, we derived n dash. N dash. Now if we can f triple dash, if we can n dash we got it as an for in a line element, n dash we will got it as a -1 by LE. Again, if you want to go for n double dash, it will vanishes. Therefore, we have to take the order of the approximation function more, or otherwise this will be converting into a such a way. So let us assuming as a f dash is h, for example. So then we can get it as a 2 equations. So you can substitute f dash in above, f triple dash means h double dash, f into f dash into f into f double dash. Therefore, f double dash means h dash. Therefore, beta into 1 minus h square, f dash square means h square we will get. And based on this, you can change the conditions above and take the variational function here. So then we can get it as a Galerkin method, that is a error function into the approximation function. So approximation function, let us say that it is a f is an approximation function, dou f by dou pi a with respect to arbitrary parameter, which must be 0. Therefore, what is the error function residue? Residue is nothing but f dash minus h. That means this equation, when you can take both, the must be residue is occurred in a differential equation. Therefore, error function is f minus h or f dash minus h or h minus f dash, whatever it may be. Then let us say that error function is 1. So another error function in this, that means e2 dash. E2 dash means you can take it as h double dash plus f h dash plus beta 1 minus h square. So the error function you can write it the right. So we can have a w1 where approximation function the dou h by dou pi I, and w2 dou f by dou pi I2, which are the approximation function for one is for h, another one is for f instead of w simply. Because if it is only one, we have assumed it as w. Now we can take it as a w1, w2. Again, take the line element, you can take as a linear triangular element. Let us say that the nodes are eta e and eta e plus 1, and from equation 5 and 6, for which you can write it as approximated function. This you can write it as a both you can write it as a Galerkin method you can take. So then here you can take it as a in the interval eta 2 eta e plus 1, this is a weighted function, and f minus h, this is a residue. This is a f minus h d eta is equal to 0 means the f minus h is nothing but a residue. Residue into weighted function. This is also residue for another sixth equation. So weighted function into residue, which are equations. So here you can take the number of the elements you can take. Let us say that two elements are there. Two approximation functions we can take it as a linear Lagrange polynomial. Therefore, here we can have a f1 psi 1 plus f2 psi 2. Because here two unknowns are there, instead of n1 u1 plus n2 u2, here we are taking as f1 psi 1 plus f2 psi 2 and h1 psi 1 plus h2 psi 2. So the like xi plus 1 xk minus x by xk minus xj, here also we have a notation like eta e plus 1 minus eta by eta e plus 1 minus eta is a Lagrange polynomial. Instead of n1 n2 n3, we are taking as a shape function size as psi 1 and psi 2. So therefore the in the interval ne to ne plus 1. So when you can find out like after obtaining all solutions, simplification, whatever we can get it as a above like. So here I will show here the above like the AE or whatever it may be. So here we can take it as a denote it as a K11, K12, so on like that. So here again we are not showing all the integrations, whatever the here we can take it as the Galerkin method, integral of the matrix whatever nj dash nk dash so on like that. That means psi here instead of n means we have taken is a psi. So psi I into psi dash, psi I into psi dash, psi I into psi I, like that whatever it may be there in the above. Psi I dash into psi I dash, psi j dash. That means nj dash nk dash, nj dash nk dash, like that. Here we have a psi I dash, psi I j dash, like that. So for which problem we will get it as a coefficient that we can ultimately at the end we will get it as a A of E. A of E means here this particular problem we have a K11, K12, because here two equations, the combined two equations we can take it which are representing K11, K12, K21, K22. So complete matrix, and the unknowns are F and H, both unknowns are here. So coupled, therefore the values on the right hand side we can have. So for only two elements we can have. So sometimes if we can write a programming and for example we divided into 1000 linear elements, so that we have solved by using the MATLAB program. For example 10 power minus 5. So we got the different B values, we got the velocity proportion like this. Now we can also go for, if you want to go for two-dimensional element, how we will get a two-dimensional value problems here, for example. So we can have a del square u is Poisson equation, del square u is -1. So mod of x less than or equal to square rectangular square network. So here we can have a, so the along the boundary the values are values. Hello.
Sir,
madam.
please complete that, sir, because of the other next madam function also there.
Okay, another 10 minutes, madam.
Yes, sir. Yes, sir.
Okay,
Sir.
Okay, right.
Thank you, sir. Sorry, sir.
Right. Now this is like we can just I will explain this two-dimensional domain. We let us divide into triangular element. So each triangular element can be taken it as a nodal point in the anti-clockwise direction. Let us say that 1, 2, 3 for first element, and next 4, 5 for second element, and 5, 6 for second element. These are called as a global nodal points, not common, global nodal. Now let us find out the polynomial function for element 1, polynomial function for element 2, polynomial function for element 3. The function, polynomial function means approximation function for each element we have to find out. But the nodal points or nodes are different for 1, 2, 3, 4, all the elements. First element, second element, third element. This we can take it as anti-clockwise direction. So therefore, let us say that we can go for first element. So triangular element, we take it as this 1, 2, 3, x1, x2, x3, and And we can have this, and already we have derived for triangular element, that is U approximation is nothing but N1, U1, N2, U2, N3, E3, so on like that. So pi of is nothing but unknowns here, U1, U2, U3. So we can take it as a the shape function N is N1, N2, N3, pi is U1, U2, U3. And then we can have a derivative of that with respect to x also. We can dou n by dou x means dou n1 by dou x, dou n2 by dou x, dou n3 by dou x. So transpose of that shape function means n1, n2, n3 column matrix. Transpose of the derivatives means dou n1 by dou x, dou n2 by dou x, dou n3 by dou x. Just I will take it as again Galerkin method. This is a weighted function. This is an approximation function. Approximation function means U of E. U of E means here you will get the shape functions N1, N2, N3 and U1, U2, U3. Therefore, we will get 3 cross 3 triangular matrix. Therefore, ultimately, when you can the residue means we can write it as instead of residue E dou U by dou pi E, we can write it as dou U by dou pi E and residue here we can write. So dou U by dou pi E we will get for example, with respect to U1, we will get N1, with respect to U2, we will get N2, with respect to U3, we will get N3. Therefore, column matrix combinedly we can write it as N transpose. N transpose means N1, N2, N3. And similarly, when you can take U of E is nothing but del square. What is U of E? U of E is nothing but here you can say that is del square E is minus 1. The del square is minus 1 means the dou square U by dou square plus dou square U by dou y square is minus 1. So when you can take minus 1 plus side, this side, that is nothing but error. Error is nothing but E of E. Therefore, here instead of E of E, that you can substitute the function. And where UE is nothing but you can take N pi. Where N pi is nothing but N1, N2, N3, N1 U1 plus N2 U2 plus N3 U3, so on like that. Therefore, we can substitute here, and then you can NT you can multiply, and you can take here this as a when you can dou n pi by dou x square. Dou n pi by dou x square means n pi means with respect to n1, n2, n3, with respect to you can take, and we will get in the particular form of this. So when you can integrating this UV form integration, when we will get this into a particular form, and you can push the known functions the right side, you can push on a typical element, let us say that typical element sigma e. Again, whatever I have shown, instead of this, this means n means n transpose means column matrix of dou n1 by dou x, dou n1 by dou y, like that dou n1 by dou x, dou n1 by dou x, dou n2 by dou x, dou n3 by dou x. Here it is like that. One is column matrix, one is matrix vector row matrix. Therefore, you can multiply, you will get 3 cross 3 matrix. Therefore, that you will get integral of dou n1 by dou x, dou n1 by dou x plus dou n1 by dou y with respect to y. This dou n1 by dou y, dou n1 by dou y, like that all 3 cross 3 9 matrix you will get, and we have to simplify this. Ultimately, we know that shape functions already we derived there. So n1, n2, n3 triangular element, the area of del E we know that, where x1, x2, x3 we get it as for each one, where we know that what is the x2 y3 minus x3 y2 denoted as a1, this is v1, this is c1. In terms of that, if we can write a can be taken into particular form where n1, n2, n3 is there. So we have to find out a1, b1, c1, a2, b2, c2, so on like that. If we have go for particular type of one element, that one element means here you can say that particular element we can have here this particular element. So I will show the figure here. Particular element, here you can say that this particular element means here you can say that this is 0 to 1. So here x coordinates are 1 comma 1, here it is half comma half. So the here the xj, for example, here first nodal xj can be taken as a 1 1, xj xk x1 y1 is 1 1, x2 y2 is half comma half, here 1 comma 0. So like that you can take and simplify. So we can get it, we can simplify in this one, and we will get it as the values, and del of E you can find out. We know that x1, x2, x3 means you can simplify, and we will get this a1, b1 we will get a1, b1 for here u1, u2, u3. Similarly, you can go for a2, you can simplify, we will get a2, and similarly we can go for a3, we will get a3 and a4. But the thing is, for A1, the arbitrary parameters are the element is for U2, U3, U1, here U4, U5, U2, and here U5, U6, U2. Therefore, but we cannot, because unknowns are U1, U2, U3, U4, U5, U6, we cannot be add directly. First, we have to write into a 6x6 matrix. So all you can write into a 6x, we have to assemble all the elements, but all the elements are not the coefficient of same A, U1, U2, U3 in a sequential form, for which we have to take like this the corresponding each element, and we have to order into U1, U2, U3 or each U1, U2, U3, for which you can corresponding columns and rows you can change according to that. You can change, you can write it, and then only we can add, otherwise it is not possible. So then you can after adding this interchanging this rows corresponding rows with respect to that, and if you want to add, you can add directly. To avoid confusion, what you will do, you can write all into a 6x6 matrix. That means here U1, U2, U3 is there, U4, U5, U6 is not there. Therefore, last three rows, last three columns, you can keep it as a 6, like that. The corresponding U1 is not here in the this. You can first column, first row, you can keep it as 0, like that. You can take all and you can add all, and you will get 6x6 matrix. And we know that the boundary condition on the boundary, it is 0. On the boundary means the right side, whatever the nodes are there, U1, U3, which are zeros, and then you can incorporate the boundary conditions, then we will get it. And the right side V1 also we can find out the respective of that, you can add. So then we will get this, you can add this. So this is one method, one dimensional, two dimensional, when we'll get cell. This is for example for to understanding that. And just 2 minutes, madam, just I will close down. So because we have some problems, we did this already published work, and we can also extended this heat and mass transfer convection flow by through a cavity. When there is a cavity, there is a convection is there. In that we can have a nanofluids. Sometimes we can also take microorganics and organs, microorganics with nanofluids to control the temperature, or control the system. So the equations also we can extend. But why we want to go for this all it means many research scholars are doing with the generally we know that this converting into the stream function and above equations we can convert, and like that we can just 1 minute, madam. So the applying the methods similarly, but it is not simple. We can go for the streamlines and the isotherms and isoconcentration profiles, so we can analyze. But because there is no time, it is not possible to go for explaining the result and all. So, but the thing is, only the many authors, many research scholars are doing the standard, the Rengikutta method, shooting method, Keller-Box methods. That means you are converting into partial differential equation into one-dimensional, then you are solving. But why not going for directly two-dimensional problems? Then you can analyze the flow or heat transfer analysis completely picture you can analyze instead of after converting into the one-dimensional. This is the only possible. So either a finite element method or finite difference method, or you can have a the finite value method. Nowadays many researchers are doing finite value method, which is a good method, but the programming code is very complicated. If you can understood properly the method and the code, then it is very easy. Then only you will have a good publications. In a fluid mechanics, all the Keller-Box method, Rengikutta methods, everybody using with the ready-madely BVP4, but these are also alternative methods for good publications or good work. So with this, I will conclude my talk, which is not a research paper. I am not proposed. Just I want to give that some basics on particularly finite element methods or computational methods, because many people will not go for these methods because it is a complicated little bit. Anyway, thank you the organizers for giving me this opportunity. Thank you, one and all. Madam.
Any questions?
Anybody? Any doubts or any?
Thank you, sir, Professor sir. For explaining actually a talk on finite element analysis for heat and fluid flow. Sir explained the need of finite element method, introduction to finite element analysis, fundamental concepts of finite method, common sources of errors in FEM, common types of elements, methods of accuracy in finite method, competition, two-dimensional discretization using triangular depth, two different approaches of being in a finite element method, weighted residual methods, variation methods, one-dimensional elements, two-dimensional elements, triangular elements. Finite element solution for one-dimensional boundary value problem, two-dimensional boundary value problem. Very nicely explained, sir.
Thank you, sir. Thank you.
Sir, it was a very informative lecture upon young researchers. And this finite method is in our university, one of the
Okay.
chapters, sir. So,
Definite, sir. Definite.
now I request Dr.G.Kathyayani, madam, to read the report of India's International Symposium and what of that.
Thank you, Sreenivasa. Once again, good afternoon to all. Brief report of an international symposium. We, the Department of Applied Mathematics, organized an international symposium entitled Mathematical Sciences and Their Applications 2022 in Vemana. On the eve of superannuation of our beloved senior post professor, head Dean Faculty of Sciences, Prof.T.Vasanthi, Madhavi. On 28 January, the symposium is started with a welcome note of all distinguished dignitaries, speakers, guests, participants, research scholars, and students by Dr. Suneetha, Assistant Professor, Department of Applied Mathematics, followed by the University Innovation Center. And Dr. Kathyayani, that is myself, has spoken about the theme of the symposium, and our beloved Vice Chancellor, Professor Madhavi, in her valuable speech quoted that math is very rare, and its impact in the present scenario. Research Professor Garu and the in-charge principal Professor Chitra gave us an inspired speech and motivated us. Our beloved Professor P.Vasanthi, head Department of Applied Mathematics, explained us the importance of mathematics and how one can apply mathematics in our day-to-day life and its importance in collaborative research. Dr. S. Suneetha introduced the speaker, Dr. Sreedhar Babu, Associate Professor from Fiji National University, Fiji. Sir explained us clearly about the applications of algebra, number theory, field theory in cryptography, isogenic based post quantum cryptography, and the importance of digital signature scheme. Dr. L. Madhavi introduced Dr. G.P.Sreenivasa, Professor, Department of Mathematics, IIT Kadapa. Sir started with an encouraging note to postgraduate level, extended his concept to research level with an example relating human knee joint and mathematical bonding in terms of contribution porosity with the title Review on Analytic and Semi-Analytic Methods to Solve PDEs, Application to Lubrication Process inside a Human Keynote. The program was concluded by Dr. Madhavi with vote of thanks. Next day, Dr. L. Madhavi started the program with the welcome note addressing and inviting all dignitaries, research speakers, and participants, followed by the University Innovation Center. Dr. B.Sreenivasa Reddy introduced Dr. N.K. Professor of Mathematics, Osmania University, Hyderabad, with a brief profile. Sir explained finite element method for heat and fluid flow. Kishan sir covered basis of FEM and foundation of fundamental conditions and their methods, how to analyze and how to solve it in step by step neatly. Really, it is very useful for the present PG students. Dr. Sreedhar Babu invited Dr. S. Sreedhar, former professor of mathematics at SB University, Tirupati. Sir gave a talk on influence of elasticity and peristaltic on biofluid flows. Sir explained about the first basic problem pipe flow using the famous Hagen-Poisson law by Linod Marek Poisson moving Hagen, and also the importance of Poisson law, power law fluid, Carson fluid. He ended his talk by a brief explanation the models related to sanitary flow biomedical fluids. Thank you to one all. Before conducting the sessions, I take the proposing vote of thanks. On behalf of the Department of Applied Mathematics, our special thanks to today's chief guest, Honorable Vice Chancellor, Professor M. Sreedhar, despite her prior schedule and commitments, Madam made her gracious presence and motivated us with her encouraging words. Thank you, Madam. We are extremely thankful to today's guest of honor, Professor Vijayaraghavan Register, for his support, spontaneous support and encouragement in conducting this event. Thank you, sir. We are extremely heartfelt thanks to our principal in charge, Professor Chindramati Shankar, for her constant support in organizing this symposium successfully. We owe our special gratitude to our distinguished speakers, Professor G.P. Rashekar sir, Professor Maheshwar Rao Madhavi, Professor V.N. Krishnan sir, and Professor Srinath sir, their encouraging research-oriented address. I take the opportunity to extend our most sincere thanks and deep sense of appreciation to our beloved head and dean faculty of sciences, Professor P.Vasanthi Madam. Thank you, ma'am. Organizing committee members, my colleagues, Dr.M.Sreedhar Babu, Dr. Sreenivasa Reddy, and Dr. Madhavi, and Dr. Sreenivasa Reddy, and Dr. Suneetha, supporting staff, Mrs. Naveshwari, Achama, faculty from other universities, IT advisor, Professor Y. Nazir Ahmad, and IT team, Mr. Anil, Vinay, Neeraj. Thank you so much for your continuous support. I extend my thanks to our research scholars, students, and participants. Thank you so much. PRO, Subbareddy Garu, Shyam Swarup Garu, photographer, Oblesh, print and electronic media, Suresh. Thank you so much for your support. Once again, I thank you all for your attention. Thank you. Kindly fill feedback form. Feedback link in feedback link. We receive certificate within 10 days. Kindly fill your mail ID correctly. Otherwise, we can't connect your certificate. Now, national anthem. Yes. Thank you all. Thank you all. Thank you all. Thank you all. Kishan sir, thank you. Kishan sir, thank you so much, sir. Thank you, sir. I'm happy to sir. Thank you. Now we are going. Now, other requested to afternoon exactly 2:30 in this same hall. We are felicitating our head madam. Thank you. Sir, thank you, sir. Sir, mute చేసుకోండి. Sir, unmute yourself, sir. Unmute yourself, sir. Your voice is not clear, sir. Unmute. Kishan, sir. అయ్యో మాట్లాడుతూనే
చెప్తున్నారు ఆయన మాట్లాడితే ఆయన
రికార్డింగ్ స్టాప్.
సరే. అయ్యో ఆయన మాట్లాడినారు
ఇక్కడ
సార్ విషయం సార్ మీరు అడ్మిట్ చేసుకోలేదు సార్, అది అడ్మిట్ చేయలేదు.
అదే ఏదో చెప్తూనే ఉన్నారు ఆయన. చేసే క్లోజ్ వద్దులే, ఫోన్ చేస్తాను లేదు చేసి చేసి సార్ కూడా రికార్డింగ్ అయిపోయింది కదా, రికార్డ్ స్టార్ట్ చేసి